Okay, gang, welcome back. Happy Friday. Just a quick look at our syllabus calendar. We'll pretty much start every class by looking at this so that we know where we are and where we're headed. Today is September 9th. It's class number 2. We're covering modeling sets and absolute value, a bunch of different kinds of topics today. Just a heads up that next class, that's this coming Monday, Project 1 is assigned. You don't currently have Project 1. I will hand it to you on Monday. It will be due on September 16th, okay? Any questions on the calendar? Okay, so we are here on page 5. Basic thing that we're going to do when we come in, whether it's like right on time that you get here or even a few minutes early, is start every class with these preview exercises. If you have a chance to look at them before class, like as part of homework, that's great. But if you haven't looked at it yet, that's okay too. So with your neighbors, you're going to spend just a few minutes, get through as many of the questions on this page as possible, and then we'll come back together real soon. Go ahead. But let's talk about this graph right here. First of all, what's the name of this graph with all the rectangles? Bar graph, right? It's a bar graph because we've got these rectangular bars. Okay, observations. Let's start here. What did you say about? Tuition increases as the years increase. Everyone agree? Definitely an upward trend here. What did you guys decide about that trend? It's not a linear growth rate, right? If it were something linear, then I guess we should be able to draw a straight line that perfectly hits all of these rectangles, or maybe one corner for all the rectangles, and it's not. It is not a linear growth rate, not a constant growth rate. Is it growing fast and then slow, or slow and then fast? Slow and then fast, right? There's this curve that kind of underlies here that, I mean, that's not perfectly drawn, but there's something there where it is kind of slow growth in the beginning and then faster near the end. Okay, all good. Trevor, you said something about the value.
Oh, yeah, I said that
More than doubles over the period of this graph, right? Starting at about 3362 and ending at, what does that say, 7,000 and change? Yeah, more than doubling over the course of, I guess, 10 or 11 years, maybe. Yeah, that's pretty quick. Any other observations? Aaron?
It really shut off
All right, so a very big jump there, $600 on something that was originally 4,000. So maybe that's the biggest percentage increase right there. Yeah, lots of things that we can say just looking at the picture. It's one of the benefits of having the graphical data. I could have just given you a table of values, not the graph, but just exactly the same information in a table. It would have been much harder to make these observations with just the numbers. Okay, then there's this kind of funny squiggly thing over here. I don't know what the name of that squiggly thing is. Maybe it has some mathematical name, but more important to me is what it stands for. Why is it there? Matt?
So we just skip from 0 to 3,000.
Yeah, right. I mean, the graph, like if you're seeing these parts of our two axes, you gotta assume that this is the point 0, 0, right? It's just part of the way that we interpret those lines in that first quadrant. But if we wanted to skip a bunch of this stuff like 0 to 3,000, then we put that little squiggly thing in there just to call the attention to the reader. Hey, we're not starting at 0, 0, so this might be a little bit misleading if you're not aware of that. In fact, if we were starting at 0, 0, then this 3,000, let's see, just trying to keep scale. So 3,000, so maybe down there someplace is roughly the 0 line, the x-axis. And so what would that do? Imagine that we, like we have this whole graph, so the bars are all going to get longer. They're just all going to sweep down to this bottom line. But I want the picture to be the same size. So now you got to imagine zooming out just a little bit so it kind of gets smaller. What's that going to do to the kind of relative heights of these rectangles, like relative to each other? Is that right? Are the differences going to be expanded when I zoom out on this picture? They're actually going to they're going to kind of disappear. Like if you have to zoom out on this picture, these differences, these vertical differences that we can readily see, they become less pronounced, right? And imagine that wasn't 3,000 there, but that was 3 million. And so now imagine that this horizontal x-axis is in the basement of this building someplace, and now we really zoom out. What are the tops of these rectangles going to look like? Pretty much a horizontal, right? I mean, the difference between, you know, like 3,400,000 and 3 million, where are we? 3,400,000 and like 3,487,000. If you're looking way zoomed out, is not all that much. And so it's just something to be aware of. You don't want to be misled. It's not lying to you, but you just got to be aware of that little kind of funny squiggle and what it represents. Okay, and then down here, question. Alexis, what was your question? Yeah, what's causing this price increase? Other questions? Yeah, Ivy.
This is tuition and how much of it is fee.
Good. Tuition is different from fees. Maybe they just both appear on your bill, but maybe we want to know which is which. Other questions? How about this question? What can you expect to pay if these trends continue next year? Or what did your parents pay, you know, 30 years ago or whenever they went to school, right? These are questions that we could ask. If the trends continued, what was happening in the past? What could we expect in the future? That's what we're going to get after today. Next page, our teaching demo. Okay, so the good news is it may be possible to answer your questions using mathematics. We can work with the real data collected and presented in the bar graph to find a mathematical model, or more simply a model. And so we're going to work with today as a model. A model is a mathematical representation such as an equation or formula of a real world situation. I'll say again, for us, a model is very often going to be an equation. Model, equation. If we can describe the relationship between two or more quantities, in this case, what was on the horizontal axis? Was the years, so time. What was on the vertical axis? Was tuition measured in dollars. So if we can describe the relationship between two quantities, time and cost, we can write an equation relating them. This is an important step in problem solving, being able to convert a description of a relationship into an equation, because we have all kinds of fancy tools that we can apply to equations. And so the goal is to maybe get an equation. All right, so a quick detour from the packet here. I'm going to open up this file right here. There's a piece of free mathematical software called Geogebra. That's what you're looking at right here. It is something that you guys are going to be using a bunch in your first project. I will give you handouts with detailed instructions on how to use it. Again, it is free and it's really cool. So this is our first time looking at it together. Okay, so my colleague made this thing here. Her name is Linda, and the first thing that she did is typed in all the data here in the Excel-looking spreadsheet thing over here on the right-hand side. This is just read off of the graph, right? Technically, though, the graph didn't start 0, 1, 2. What were the numbers in your graph? So 2000, 2001, 2002. You're welcome to type those numbers in. She chose to type in these numbers and make it clear that we're starting years from 2000 is what this first column is. And then the dollar amounts are here in column B. You click a couple of buttons and get Excel to plot those points. Now these are exactly the same as the rectangles, except it's points. It's just like a point at the very tip top. Maybe it's the top left point of each rectangle. Maybe it's the top right. I have to think about it. But it's just points representing the tops of each rectangles. There? And you can see, again, is there a straight line that perfectly hits all of the data? No. But there is a line that comes as close as possible to all of the data points. Now that is a very wishy-washy phrase for a math teacher to use, as close as possible. Not going to get into the details, but it is a very well-defined thing. There is a best line, a best fit line that is mathematically as close as possible to all the points. We're not going to talk about how to calculate it in this class, but it's pretty darn easy to ask this piece of software to find it. The equation, I'll move this over a little bit. The equation of the best line for those data points is this, y equals. Now you guys have a lot of experience with y equals mx plus b. So the m and the b are these numbers here, 385 and about 3,000 and change. And so if I show you that, let's come back here. If I show you that line, it is there. Does that line perfectly hit all the points? No. Does that line perfectly hit any of the points? Looks kind of, it looks maybe like it hits J. I think it's off a little bit on B. To be honest, the likelihood that it perfectly hits any of these points is pretty much nil, but it's darn close to all of them, right? And turns out that's the best line. Okay, I'm going to hide that line for just a second. Another possibility is to, instead of finding the best line, is to find the best parabola. With your arms, use both arms. Can you guys show me what a parabola looks like? Don't be shy, we're moving the blood, get the blood flowing. Come on, and now I know that we all look ridiculous, but the people doing nothing look more ridiculous when the rest of us are holding up fingers, right? So a parabola is something like this. What if the parabola had a negative in the front of it? What would it look like with your arms? If it had a negative in the front of the x squared, yeah, maybe like that or that, something like that. Right. So what do you think? Does this look like a parabola, like points on a parabola? Not to me either. I mean, I'm imagining a parabola coming down here and then going up here, and it really does not look like a good fit. Even an upside down parabola doesn't look like a good fit. But this software can find the quote unquote best parabola, and it's easy to just type in a command and have it do it. So I'm going to do that right here. There's the best parabola. How's it look? Does it look like it's very close to the points? It sure does. Now, this is not the parabola I was envisioning, upside down or right side up. And in fact, it doesn't really hardly look like a parabola at all. It looks very straight, but it does have a slight curve to it. And if I zoom out, zoom out, zoom out, does it look like what you guys were just holding up with your arms a moment ago? It does. And so, yeah, I mean, it is a parabola, but it's just that this vertex is what it's called, this bottom point, is just way far away from the data. So we're really looking kind of far out on one of the like sides of the parabola where the parabola is kind of straight if you're zoomed in just right. So there's our parabola. I'm going to show you the line as well. And you can see that the line and the parabola are not that far apart from each other, which is maybe a surprise because parabolas are pretty darn curvy and lines are anything but curvy. But really zoomed in, they can be quite close to each other. And again, you can see that even though they're close to each other near the points, they're dramatically different from each other when you zoom out, right? Okay, and so on your packet, which is where we're headed next, we're going to play around with the equation for this parabola. Now, I can show it to you here. It's this guy right here. You guys maybe know parabolas from a past math class have x squareds in them. So that's this guy right here. So forget about this f parentheses x. We'll just pretend that's a y equals for right now. So it's a y equals 4.39x squared plus 341x plus 3,000 and change. And I think that's what's written down over here, rounded a little bit, okay? So let's come back to this packet here. Number 3, there's our formula. T standing for what? Nope. Tuition, T for tuition, and X is got to be the time. Now, honestly, the person that writes this thing in the packet is their job to tell you what the variables stand for, and it's written out here. We just have to read it. Average cost of tuition and fees is T, college year ending X years after 2000. Right? And without that information, you guys are just guessing, and that's not fair to you. On the flip side, when you are doing homework and you are taking tests and writing projects, it is your job to make clear to me what your letters stand for. Because there are about 20 of you, and you might choose 20 different sets of letters, and it's not fair to me to make me guess what your letters stand for. So this will be an important part of all of the word problems that we solve, clearly defining those variables. Okay, part A. Use the formula, that's this T equals, to find the average cost of tuition and fees year ending 2010. So is this 2010 going to become a T or an X? That is an X. But remember, X is years since or after 2000. So how many years after 2000? 10. So all we're going to do is change X to 10. So we go T equals 4 times 10 squared plus 341 times 10 plus 3194. Yeah, Ivy. Okay. All right, so I don't need 20 people typing this in, just a couple to get confirmation. The rest of us, while we're waiting on this number, are moving on to part B. So just 1 or 2 people with a calculator. I see one up here. By how much does the formula underestimate or overestimate the actual cost shown in the bar graph? Okay, so looking at the bar graph, what is the actual cost? 7, what is it? 7,004. Everybody agree? Is that the 2010 number? Good. Aaron, do you have a,
I have the same.
what did you get for this blue calculation?
Oh, it was 7,000.
Oh, it was exact. Is it?
It was 7,000. That's from the graph.
Thank you. Okay, so 7,020 was from the graph. This blue calculation was 7,004. Is that what you were saying, Matt? Okay, sorry, I misunderstood. So the blue is from the formula. The purple is from the graph. Does the formula under or overestimate the actual cost? It underestimates. And this is just about perspective, right? One of them overestimates the other and one of them underestimates. So just make sure you're reading carefully. In this case, it is an underestimate by how much? $16. That's really not too far off in the grand scheme of things, right? Compared to that $7,000 bill, off by only 16, that's not bad. Okay, let's use the model. Again, model and formula, model or equation are kind of our synonyms, to predict the average cost in tuition for the year 2014. Now this is sort of a strange question because we are in the year 2016 and I'm asking you to predict from the year 2014, but why is the word predict right for this problem? Yeah, the bar graph only goes up to 2010. So it is a prediction relative to all the information that we have. Okay, so 2014, so that means x equals what number? 14 there. 1990. This is going before the year 2000, so what is it? -10. Yeah, don't be shy about getting those negatives in. Okay, so let's get a few more calculators here. If you've got one, even if it's on your cell phone, it is rarely okay for that cell phone to be out, but this is one of those times. So I don't need you to do both. Maybe half of you do one and half do the other. Let's see if we can't get some numbers up here.